This lesson is the fourth part in a series covering some basic statistical functions that come in useful in the engineering world, particularly when it comes to taking measurements and understanding what those measurements mean. Today we'll be looking at the empirical rule, which is a statistical phenomenon that typically happens whenever many measurements are taken and data is found to be normally distributed. Using the empirical rule, we can begin to infer statistics about a larger population using data gathered from just a small sample. This starts to take us outside of the world of summary statistics and into the world of inferential statistics. To better understand normal distribution, let's take a look at what happens when distribution is left to random chance. In this scenario, there are 5 slots. The purple dots represent pegs, and the orange dot represents a marble being dropped onto the peg. Each time a marble hits a peg, it has an equal likelihood of going left or going right. So in this example, the chances of the marble landing in slot 1 or slot 2 are 50-50. If 2 marbles were dropped onto this pegboard, it's statistically likely that one would land in slot 1 and one would land in slot 2. Now let's expand the pegboard a bit. This time, the marble could drop into slot 1, 2, or 3. There's only one path that the marble could take to slot 1. It would need to bounce left both times. The probability of the marble landing in slot 3 is the same. It would have to bounce right both times. However, there are 2 possible paths that the marble could take to get to slot 2. It could bounce left, then right, or it could bounce right and then left. So the probability of the marble landing in slot 2 is twice as great as landing either in slot 1 or in slot 3. If 4 marbles were dropped into this pegboard, we would expect to see 1 land in slot 1, 2 land in slot 2, and 1 land in slot 3. Now let's expand the pegboard some more. In this case, there is still only one way for the marble to get into slot number 1. It would have to bounce left 4 times in a row, which is statistically possible, but unlikely. The same goes for slot 5. The marble would have to bounce right 4 times in a row to land in slot 5. There are 4 possible ways for the marble to land in slot 2. It might bounce left, 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 right, left, left, right, left, left, right, left, left, or right, left, left, left. The same holds true for slot 4, with the 4 possible paths being on the other side of the pegboard. There are even more possible ways for the marble to find its way to slot number 3. If it starts by bouncing left from the first peg, then it could bounce left, left, right, right, left, right, left, right, left, right, right, left, or it could take another 3 possible paths if it bounced right from the first peg, resulting in 6 different possible paths from the top to slot number 3. So when multiple events are left to random chance, it's statistically likely that there will be more occurrences near the average and fewer occurrences that are much higher or lower than the average. The more we expand the pegboard, the more clearly we can see that our marble data is normally distributed or forms a bell curve. The same thing tends to happen whenever many measurements are taken of things that are supposed to be about the same. There's always some variation in the measurements. Most will be near average, but maybe a little higher or a little lower, and few will be further from the average. But when the measurements are graphed, they will normally form a bell shape. When a dataset is normally distributed, we can apply the empirical rule. When data is normally distributed, the empirical rule says that almost all data will fall within 3 standard deviations of the mean. Many quantities tend to follow a normal distribution: heights of people, test scores, errors in measurement, and so on. Given normally distributed data, 68% of the data values should fall within 1 standard deviation of the mean. 95% should fall within 2 standard deviations of the mean, and 99.7% should fall within 3 standard deviations of the mean. This is referred to as the empirical rule. Of course, with small samples or populations, these percentages may not hold exactly true because the number of values will not allow divisions to this precision. To use the example of the marbles in the pegboard, if 100 marbles were dropped into a large enough pegboard, 68 of them would fall within 1 standard deviation, 95 of them would fall within 2 standard deviations of the mean, and only 5 out of 100 marbles would fall outside of this. Of course, it is possible that an abnormal number of marbles bounce too far to the left or too far to the right on any given attempt, but the statistical probability in any given trial should result in a normal distribution that follows the empirical rule. Let's assume that this data was gathered from a sample taken from a larger population, and that we are interested in finding statistics for that larger population. The sample data values are fairly evenly distributed about the mean. Approximately 50% of data values fall below the mean, and approximately 50% fall above the mean. And the frequency of occurrence decreases as the value of the data point moves farther away from the mean. The data appears to form a bell-shaped curve. This data set looks to be normally distributed. The mean is 0.08. The sample standard deviation formula is used to estimate the standard deviation of the larger population and is found to be 1.77. Since the data appears to be normally distributed, we can estimate that approximately 68% of the population data will fall within 1 standard deviation of the mean. In other words, 68% of data will fall within the range of 1 standard deviation below the mean to 1 standard deviation above. If we add the standard deviation, 1.77, to the mean, 0.08, we find the upper limit of this range, 1.88. If we subtract 1 standard deviation from the mean, we find the lower end of this range, negative 1.69. This tells us that 68%, or about 2/3 of the data, will fall between negative 1.69 and 1.88. And again, because the data is assumed to be normally distributed, we can estimate that 95% of the population data will fall within 2 standard deviations of the mean. So when we double the standard deviation to 3.54 and then add and subtract that number from the mean, we find the upper and lower limits of the range that includes 95% of our data. The range is wider, but it accounts for a larger percent of possible outcomes. So approximately 95% of the data will fall between negative 3.46 and 3.62. Let's apply the empirical rule to a real-life scenario. Mr. Dillman throws a rock 10 times and records each distance. Using this sample data, predict the range of travel distances within which 68% and 95% of rocks would fall. After 10 throws, the following statistics were found. The mean distance of the throws was 29.36 feet, and the standard deviation of the throws was 1.31 feet. Here's the histogram representing the 10 practice throws. We can see that the data is fairly normally distributed. So according to the empirical rule, 68% of throws should fall between 1 standard deviation below the mean and 1 standard deviation above the mean. To find these limits, we subtract 1 standard deviation from the mean, and we add 1 standard deviation to the mean, and we find a lower limit of 28.05 feet and an upper limit of 30.69 feet. This range is our 68% confidence interval, so we can say with accuracy that approximately 68% of throws will land between 28.05 and 30.69 feet. To find the 95% confidence interval, or the range of distances that will include 95% of throws, we need to expand the window a little wider. In this case, we need to subtract 2 standard deviations from the mean and find the lower limit, and add 2 to find the upper limit. When we do the math, we can say with accuracy that approximately 95% of throws will land between 26.74 feet and 31.98 feet. The range is wider, but it encompasses a much greater percentage of possible outcomes. Reporting confidence intervals like this is a reliable way of making accurate claims about a measurement. Since measurements are only best estimates and are subject to error based on numerous factors, it would be misleading to report a measurement simply as a single value, an average of the possibilities. It would be much more accurate to give a range, such as a confidence interval. So if a manufacturer produces machine parts and must accurately communicate the length of the parts to the customers, the most accurate way might be to measure a sample of products and use the resulting statistics to state that 95% of products will fall between a certain lower and upper limit. That way customers can be sure of the typical part size and the possible variation that might occur. Thanks for watching. To find out more about how inferential statistics can be used to determine the precision and accuracy of measurements, check out Part 5 of this series, Precision and Accuracy of Measurement.